Welcome to my channel on data analytics. In this video, we are going to cover a basic clustering algorithm called kMeans. We will be covering this algorithm in depth with an example. We will also provide a demo of the kMeans clustering algorithm using the real world data. For demonstration purposes, we are going to use Python language and the working environment will be Colab. The library from which we are going to use the k-means algorithm is scikit. Given the steps involved in knowledge discovery in data, this video covers clustering technique, which is an important data analytical technique. Data analytical techniques constitute of several learning algorithms that can help us to build knowledge bases from the data. Learning algorithms are basically two types. The first category of learning algorithms are called learning from knowledge base. That is, a user will provide the knowledge base and the algorithm will use the provided knowledge base for decision making purposes. The another category of learning algorithms are learning from the data. So these algorithms are broadly classified into three types: unsupervised learning, supervised learning, and semi-supervised learning. In unsupervised learning, user will simply provide the data and request the algorithm to learn by itself. He will not provide any additional data. So, when we are talking about unsupervised learning techniques, there are only two types. The first one is pattern mining or association rule mining techniques, which try to discover patterns from the given data. This topic has already been covered in this channel. Please check the link shown above to learn about pattern mining. The second category of unsupervised learning techniques is clustering. In this video, we are going to talk about a fundamental clustering technique called k-means. A key question that comes in mind to the users is why clustering is called an unsupervised technique. The answer is very simple. In the clustering technique, the user will provide the data to the clustering algorithm and he will simply ask the algorithm to group the given data into various clusters. The algorithm by itself has to understand the data and accordingly it has to group the given data into clusters. Since user is simply providing the data and he is not providing any further information about the data, we call a clustering algorithm an unsupervised learning algorithm. The basic clustering techniques are broadly classified into four types. The first class of clustering techniques are called centroid based clustering algorithms. These algorithms organize the given data into non hierarchical clusters. The strength of these algorithms is that they are very easy to implement and they are often efficient. But the weaknesses of these algorithms is that they are sensitive to initial conditions, outliers, and more importantly, centroid based algorithms can only discover clusters that are of circular shapes because of the distance function they use. A classic example of a centroid based clustering is kMeans, which is very widely used in the real world applications. The second class of clustering techniques is density based clustering. These techniques use the connections of areas based on the high density of the objects to create clusters. Density based algorithms can find arbitrary shaped clusters as long as the density areas are connected. A key weakness of these algorithms is in high dimensional datasets. Generally, density based clustering techniques do not work well in high dimensional data. That is, if a dataset has too many attributes, then density based clustering algorithms may not work properly. A renowned density based clustering algorithm is DBSCAN. The another type of clustering based techniques is distribution based clustering algorithms. These algorithms implicitly assume that the data follows a certain distribution such as Gaussian distribution and use these distributions to cluster the given objects within the data into clusters. The main strength of these algorithms is that if the distribution is of a dataset is known to us, then we can employ these algorithms to get better results. The weakness of these algorithms is that since real world datasets are complex and each attribute may follow different distribution, they may not work properly in certain scenarios. A classic distributed based clustering technique is called expected maximization. The final category of clustering techniques is hierarchical based clustering. So, these algorithms create hierarchy of the given data. Mostly ontology based datasets use this hierarchical clustering algorithms. This a fundamental limitation of this hierarchical clustering algorithms is to finding the stopping point. Two examples of these hierarchical clustering algorithms are agglomerative clustering algorithm and divisive clustering algorithm. In this video, we are going to cover kMeans algorithm. We will cover DB scan, expected maximization, agglomerative and divisive clustering algorithms in the later videos. The outline of this video is as follows. First, we introduce the basic terminology needed to understand the k-means algorithm. Next, we discuss the working of k-means algorithm. Later, using a sample dataset, we illustrate the working of k-means algorithm by step. Next, we discuss the limitations and the solutions presented to address them. Finally, we provide the demo of k-means algorithm using the real-world air pollution data. Let us learn the basic terminology needed to understand the working of k-means algorithm. The basic question that comes in mind to use a k-means algorithm is how the data must exist. To execute a clustering algorithm, one has to keep in mind that the data needs to be in a tabular format with rows and columns. Each row represents an object and each column represents the dimension. Can we perform clustering on the multi-dimensional data? Unfortunately, we cannot perform clustering on the multi-dimensional data. Clustering algorithms, especially centroid-based clustering algorithms such as k-means, use distance measures to determine the similarity between the objects in the given data. Thus, it is important for us to know the popular distance measures. The measures that are widely used for measuring the distances between the two objects are Euclidean distance, cosine distance, Manhattan distance, Minkowski distance, and Chebyshev distance. Generally, Euclidean and cosine distances are widely employed to measure the distance between the objects. In this video, we are going to use Euclidean distance. Please keep in mind that if the Euclidean distance between 2 points is 0, it means they are at the same location. Higher the Euclidean distance between the 2 points, farther they are from each other. In centroid based clustering algorithms such as k-means, a centroid basically represents the middle point in a given set of data points. For example, if we have the data points A, B, and so on up to Z, then The centroid of these data points is nothing but mean, median, or mode of each attribute of these data points. For example, let us assume there are three objects A, B, and C having values in 5 dimensions. Given these three objects, the centroid of these three objects represent a point which is in between A, B, and C. That is, we simply take the each attribute, calculate the mean value of the each attribute, and then we put them here. So this represents the centroid. Iteration means a number of times a particular loop has executed. For example, if we say iteration equivalent to 1, it means a loop containing a set of functions was executed only once. Similarly, iteration 2 means a loop has executed twice. Iteration n means a loop has executed n times. We will now learn the working of kMeans algorithm. The flowchart of kMeans algorithm is shown here. Once the user provides the dataset and specifies the total number of clusters needed from a dataset, the k-means algorithm iteratively performs the 4 steps to identify the clusters within the dataset. First, we identify the centroids that exist in the data. We do this either by randomly selecting the data points or creating virtual centroids using the mean values of objects. Next, calculate the distances between the objects and the centroids. We assign objects to centroids based on the minimum distance criteria. The final step in the k-means algorithm involves either ending the algorithm or performing the entire iteration one more time. So this step basically involves two substeps. First one, if the number of iterations reach a particular threshold value, then we end the algorithm. Otherwise, we check if the objects within the clusters have moved or not. If the objects within the clusters did not change between two iterations, then we assume that we have reached good clusters and we end the algorithm. We now illustrate the working of k-means algorithm with an example. In this example, we will consider the weight and height of the 4 persons and input it to the k-means algorithm and request the algorithm to cluster the given data into 2 clusters. We will now see how k-means algorithm performs clustering on this dataset. First, let us visualize the given dataset using a graph. Let the x-axis represents the weight of a person and the y-axis represents the height of a person. The first person's height and weight are 1 and 1 respectively. Thus, we put a point at 1 comma 1. Similarly, we keep a point at 2 comma 1 to represent the person 2. Similarly, we keep points for P3 and P4 persons. Given this data, we now apply kMeans algorithm to perform clustering. The working of the kMeans algorithm is given here. We will now perform step-by-step process to cluster the given data. We start the k-means algorithm by specifying k value equivalent to 2. Next, we come down here and we start the iteration by setting its value equivalent to 1. In the first iteration, we first take the 4 given persons data. Next, we start with the step 1, that is identifying the centroids. Until now, we do not have any information about the centroids. So, we first randomly select the centroids from the given data. Let us choose initial centroids, say P1 and P2. Once we select the initial centroids, we use its data as the centroids. Once we finish this step, next we calculate the distances between the centroids and the points. For calculating the distance, we use the Euclidean measure. Please keep in mind that we have to calculate distance between every centroid to all points. Once we calculate the Euclidean distance, next we move to the next step, that is grouping the data points based on minimum distance. In this step, we choose each data point and then we find the minimum value, that is which point is close to a centroid. We can see that P1 is close to C1. So, we say that P1 point belongs to C1 centroid. Similarly, we choose another point P2, check the closeness of this point with respect to C1 and C2. We can see that P2 is close to C2. So, we keep the point P2 to C1. In other words, we say that P2 is grouped to the centroid C2. Similarly, we choose the point P3 and assign it to C2 because the value of P3 is close to C2. Similarly, P4 will be assigned to C2. Once we complete this step, we move to the final step where we try to decide whether we can end the algorithm or perform one more iteration. Since this is the first iteration where points were assigned to the randomly selected centroids, we generally perform one more iteration by setting iteration equivalent to 2. In the second iteration, we have to once again need to find the centroids. Since centroid 1 contains only one object, that is P1, we use the data of P1 as the centroid 1. The objects P2, P3 and P4 were assigned to C2 centroid. So, we calculate the new centroid of these three objects using the mean value. The new coordinates of the C2 centroid are 3.66 and 2.66. In the figure, you can observe that while the centroid C1 still remains at P1, the centroid C2 has shifted from P2 to 3.66 to 2.66. After calculating new centroids, we once again calculate the distance between the points and the new centroids. Next, we assign the objects to the centroids based on their proximity. So, P1 and P2 are assigned to C1 while P3 and P4 are assigned to P2. In the final step, we check whether the objects in the clusters have changed or not compared to previous iteration. Since the objects have changed in the clusters, we increment the iteration and perform the kMeans algorithm. Observe that the iteration 2 changed to iteration 3. In the third iteration, we again start with the calculation of centroid. So, in this step, we go to the cluster containing the points P1 and P2 and calculate its new centroid point. Similarly, we take the cluster 2 containing the points P3 and P4 use it as the centroid of cluster C2. In the graph, please observe carefully. Previously, the cluster centroid C1 was at 1, 1, whereas cluster centroid point 2 was around 3.66 and 2.66. These centroids will now be shifted to 1.5, 1 and 4.5, 3.5. So, if we shift it, then C1 has moved and says P1 and P2 belong to cluster 1. Similarly, the centroid C2 moves up and then says P3 and P4 belong to a cluster. We choose the new centroids and then calculate the distances between all the points to every centroid. After calculating the distances, we move to the next step, that is grouping the points to each cluster based on the minimum distance. So, we have the centroids C1 and C2. For each centroid, we check the points and looking at the lowest or proximity to the centroid, we assign P1 to C1. Similarly, P2 will be assigned to C1. When we talk about P3, we can see that P3 is close to C2. So P3 will be assigned to C2, and then P4 will also be assigned to C2. After assigning points to each cluster, we move to the final step and check whether we have to end the algorithm or continue one more iteration. Since we have observed that the points in the clusters haven't changed in this third iteration, we simply stop the algorithm, and then we say that P1 and P2 belong to C1 cluster, while P3 and P4 belong to C2 cluster. This is how the kMeans algorithm performs clustering of the objects that exist in a given dataset. Now we try to understand the limitations of the k-means algorithm and the available solutions to address those limitations. An open problem faced by the k-means algorithm is how to choose the right k value for a dataset. That is, assume that I have given you the data set and requested you to perform k-means algorithm. Then the immediate question that comes into your mind is, what should be the k value to use? This question is the fundamental and the open problem faced by the k-means algorithm. To solve this open problem, researchers have suggested to use elbow k-means algorithm. So, in the elbow k-means algorithm, as shown in this picture, what we try to do is we try to run the k-means algorithm at different k values on a given dataset. Next, what we try to do is at each k value, we look at the sum of squared distances and we try to plot the graph. The figure here represents or looks like a hand of a person. So the best k value always represents the elbow point. Sometimes there will be only one k value or multiple k values. If you find multiple k values at the elbow, please try to run at all of those k values and choose the best one by yourself. In addition to elbow k-means method, we also use measures such as Shillaughty and Bayesian information criteria. Next one, this is the fundamental drawback of the k-means algorithm, which is how to select initial centroids. The reason is, since we are selecting the initial centroids randomly, we may not get the same results every time. So this is the problem with the k-means algorithm. To solve this problem, we apply k-means plus plus algorithm. Next limitation of k-means algorithm is it is sensitive to outliers that exist in the data. If your data has too many outliers, it is advisable to use k median or k-mode algorithm. Finally, the limitation of the k-means algorithm is it cannot find irregular shaped clusters. In this demo, we will learn how to use k-means algorithm to discover useful information from the data. Air pollution is a major cause for several cardiorespiratory deaths in Japan. To tackle this problem, Ministry of Environment Japan has set up a nationwide sensor network to monitor air pollution. This network is called AEROS. The AEROS system measures the pollution at hourly intervals. In this demo, we are going to use the air pollution data and try to cluster the sensors based on their pollution values. So in the demo, first what we are going to do is we are going to read the air pollution data produced by the Soramame or Aero system. So in this data, we will have the timestamp information followed by the sensors and their hourly air pollution values. What we are going to do is we are going to remove the timestamp information and then we will transpose this matrix. Once we have the transposed matrix, we will perform clustering on the sensors to identify and cluster the sensors that have recorded similar pollution levels. The source code of this demo can be found in the GitHub Introduction to Big Data at Uday Lab. Please come to this GitHub repository and check the contents. You can see that at class 7 we are covering clustering and k-means. So please visit the folder class 7 which contains a notebook file kmeans and also the dataset that we have used. Please open the notebook and click on the collab button. Once you click, the entire notebook will appear in the collab. So please download the dataset. Once you download the dataset, we are going to read the dataset into a data frame. You can see this. You can see that in this data frame, we have an unnamed column, timestamp, and then location of the sensors and the values they have recorded. Let us check the shape of the data frame. We can see that there are 40 rows and 42 columns. So what we are going to do is, in the next step, we are going to do data wrangling, where we remove the timestamp information. Next, we remove the unnamed columns. Next, what we are going to do is, you can notice that many sensors are not recording any air pollution values. So we are going to prune those sensors. Finally, what we will do is, we are going to store the sensors in a special attribute and then fill up the missing values using mean imputation. So let us drop the timestamp column from the data frame. Let us remove the columns that do not have location information of the sensors. You can see that we have removed 2 columns now. From 42 columns, we were reduced to 40 columns. The size remains the same. Now let us check how many columns have nan values. We can see that for many columns there is no pollution value. All of them are nans. So what we are going to do now is we are going to remove those columns or sensors that have less than 5% of missing values. Once we remove these sensors, we can see that we have removed half of the sensors that do not have any pollution value. Next, we are collecting the sensor location information, and then we are performing mean imputation to fill up the missing values. Please observe that in this imputation there are still negative values. Okay, but you cannot have negative values. We can remove these values and set it to 0, but we are not doing all those steps. We are simply using this data as it is, and then I am performing imputation. After imputation, we are transposing the matrix so that we can perform clustering of the sensors. Now you can see the previous matrix that is containing 40 units of data for 20 columns has changed to 20 data objects and 40 columns or dimensions. So we have transposed. Now we are going to perform clustering of these 20 objects. To perform clustering, first we need to know the k value. So we first run elbow k-means algorithm and choose the k value. So this is the elbow k-means result we got. You can observe that the result was not in the elbow shape. So we can rerun the algorithm, and now we got the different one. That is the reason. So every time we run the k-means algorithm, we may get completely different results. However, let us choose the k value as 4. So by choosing the k value 4, let us execute the algorithm. So once we execute the algorithm, we can visualize the clusters using GeoPandas and Folium. The result will be stored in the image. Once you view the image, we can see how the sensors were clustered in the data. Thank you very much for viewing our video. If you like our work, please press the like button, share it with your friends, and subscribe to our channel for more interesting videos.